All right, let's jump right in. Today, we're cracking open the chemist's toolkit. We're going to explore how scientists actually control, measure, and predict what happens in the solution. And we'll be focusing on two huge ideas: acid-base equilibria and solubility equilibria.
It really all comes down to this one big question. When you've got stuff dissolved in water, how do you take charge? How do you control what it does, measure its properties, and, maybe most importantly, predict what's going to happen next? Well, that's exactly what we're about to find out. So, here's our game plan. We're going to build this toolkit together, piece by piece. First up, we'll grab our tool for control. That's buffers. Then, we'll add the tool for measurement, which are titrations. After that, we get our crystal ball for prediction, solubility. And finally, we'll see how to put it all together to actually manipulate a chemical system.
Okay, let's get into it with our very first tool. Before you can do anything else, you've got to have control. And when it comes to chemistry and water, control is all about taming the pH of a solution.
The secret to controlling pH starts with this really cool principle called the common ion effect. Think of a reaction at equilibrium, like a perfectly balanced seesaw. Now, what happens if you add a little extra weight, in this case an ion that's already on one side? Well, the seesaw is going to tip back the other way to find its balance again. That's the common ion effect.
And this right here shows you that effect in action. It's fantastic. On the left, you've got pure acetic acid, and its pH is pretty low, 2.87. But now look at the right. We add some sodium acetate, which gives us that common acetate ion. And bam, the pH jumps all the way up to 4.44. So why did that happen? All that extra acetate forced the reaction seesaw to tip back to the left, using up hydrogen ions and making the solution way less acidic.
This is the absolute magic of a buffer. It's basically a solution with both a weak acid and its partner, the conjugate base, hanging out together. This pair acts like a chemical sponge. If you pour in some acid, the conjugate base just soaks it right up. If you add a base, the weak acid jumps in and neutralizes it. And the result? The pH barely budges. It's the reason our blood pH stays so stable. It's an incredible life-sustaining buffer system.
And this formula, this is what gives chemists their superpowers. The Henderson-Hasselbalch equation is like a cheat code. It doesn't just let us calculate the pH of a buffer, it lets us design a buffer for any specific pH we want, just by tweaking the ratio of the base and the acid. It's amazing.
All right, on to our next tool. So we know how to control a system, but how do we precisely measure what's in it? Let's say an unknown concentration. Well, the answer is a technique called titration.
I want you to think of a titration curve not as some boring graph, but as the story of a reaction, unfolding one drop at a time. Part 1 is the very beginning. Before we've added any base, the pH in our flask is just the pH of the weak acid we started with, in this case 2.87. Then, as we start adding our base, something really cool happens. We're neutralizing some of the weak acid, which means we're creating its conjugate base. Does that sound familiar? It should. We've just made a buffer right there in the beaker. This flat section is the buffer region, and it's where the pH rises really slowly and predictably. And now, for the climax of our story, the equivalence point. This is that exact moment when the amount of base we've added perfectly matches the amount of acid we started with. See that massive, almost vertical jump in pH? That's our signal. That tells us the reaction is done.
After that dramatic climax, the story starts to wind down. All the weak acid is gone, so at this point, the pH is just being controlled by the extra strong base we keep dripping in. The curve flattens out again, but this time way up high, at a very basic pH.
But hang on a second. Let's look back at that equivalence point. If we've perfectly neutralized the acid with the base, shouldn't the pH be a perfect neutral 7? So why is it clearly basic, somewhere around 8.7 in this example? That's a great question.
The answer, the culprit, is actually the product of the reaction. At the equivalence point, we've turned all our acetic acid into its conjugate base, acetate. And it turns out acetate isn't just a neutral bystander. Nope, it's a weak base itself, and it reacts with water in a process called hydrolysis, producing hydroxide ions, which of course makes the solution basic. Mystery solved. Okay, let's grab our third and final tool from the toolkit. We're going to shift gears from reactions in a solution to the limit of dissolving itself. In other words, how can we predict if we mix two liquids together, a solid is going to suddenly appear and fall out?
We predict this using something called the solubility product constant, or a KSP.
The easiest way to think about it is like a strict fullness limit for how many ions a solution can hold. For a substance like silver chloride, that number is incredibly tiny, which tells you right away this stuff does not like to dissolve in water.
So how do we use it? It's actually just a simple comparison. We calculate a value called the ion product, Q, which is just the concentration of ions we actually have at that moment. Then we compare our Q to the KSP limit. If Q is smaller than the limit, you're good, nothing happens. But if your Q is bigger than KSP, the solution is oversaturated, and you're going to see a solid precipitate form until things get back down to that KSP level.
And now, for the really fun part, let's bring everything together. We can go beyond just predicting what will happen and actually use our tools of control to manipulate whether something dissolves or precipitates out.
We have a few different levers we can pull to mess with solubility. We're going to focus on two really powerful ones. The common ion effect, hey, we've met that one before, and the pH of the solution. There's another important one, complex ion formation, but for today, we'll stick with these two. And just look how powerful that first lever is. The solubility of silver chloride in pure water is already super small. But now add a solution that already has that common silver ion in it, and the solubility just tanks. It plummets by a factor of nearly 500. It makes total sense. The system already has plenty of silver ions, so it can't dissolve nearly as much of the solid. The pH lever is just as impressive. Check this out. If you have a salt with a basic part, like magnesium hydroxide, you can actually make it dissolve more just by adding acid. The H+ ions from the acid react with and gobble up the hydroxide ions. The system then tries to rebalance itself by dissolving more of the solid to replace them. We're literally pulling the solid into solution just by changing the pH. And that's really the big takeaway here. When you understand these tools, buffers for control, titrations for measurement, and solubility rules for prediction, you go from being a passive observer of chemistry to an active director. You get to be in the driver's seat. So, I want to leave you with this final thought. If you have the power to precisely control what dissolves and what crashes out of a solution as a solid, what kind of real-world problems could you solve? I mean, everything from selectively pulling pollutants out of water to designing and building brand new materials one molecule at a time. The possibilities are truly endless.